All right, thank you all for coming for our colloquium today. It's really a joy for me to welcome Liang Jiang back here to Caltech. Liang is an old-timer at Caltech. He was an undergraduate here, graduated in 2004. He was a postdoc here between 2009 and 2012, I believe. Yeah. I had the pleasure of working rather closely with him. And then he left for a while, and now at least he's back for a bit. So Liang did his PhD at Harvard with Misha Lukin, graduated in 2009. Like I said, we had the privilege of having him here as a Price Fellow, where he was working with John's group and with my group on already things that were presaging the breadth of his research, from condensed matter to quantum information topics. He then, in 2012, joined the faculty at Yale in applied physics, where he stayed for 7 years. And then in 2019, I believe, he moved to Chicago, where he's faculty in the Institute for Molecular Engineering.
No, it's a Pritzker School of Molecular Engineering.
Pritzker School of Molecular Engineering.
Yes.
Yeah, but it's really a place where it seems to be collecting all smart people working on things that are kind of practical in physics departments elsewhere into one place with a lot of access to research funding and resources, etc. That's my fantasy about the Pritzker School. So during his career, he won many awards, amongst which are Sloan Fellowship, Packard Fellowship, and also very recently he won the Bennett and Landauer Award of the APS, recognizing his work in quantum information and quantum computing systems. His research has been remarkably broad. His contributions vary from condensed matter all the way to the theoretical end of quantum information. He contributed a lot to the design of quantum computing hardware, and his proposals for how to operate this hardware have been implemented in the leading groups pursuing quantum computers around the world. So it's a pleasure to have him here. He'll be here today and tomorrow, and his talk today about bosonic quantum information processing. Please.
Yeah. Okay. Hi everyone. Just make sure people in back row can hear me, right? Good. Yeah. So first, I'd like to thank Gil and John and others for hosting me here, and it's a great opportunity, and I'm very excited actually have a chance to come back to Caltech and meet all my previous instructors and also collaborators here at Caltech. Yeah, and this is the place where actually the quantum information kind of take off about almost more than 2 decades ago. Yeah, so it's actually a great honor to have this opportunity to talk about my kind of a recent research about how to use a bosonic system to process quantum information. And so this is actually a highly collaborative work. Maybe at the end of the talk, I will show a big slide with many people kind of collaborated in both theory and experiments. And so as a motivation, maybe I would like to first start with, I need to make sure my cursor is here. Yeah, so start with actually pointing out there are many applications in quantum information that we actually use the bosonic systems, which are basically harmonic oscillators in different forms to process quantum information for computing, or use the bosonic modes for communication, and the gravitational wave detectors, they are resonators, also bosonic modes, and also sampling and simulations, which are also using bosonic modes. But one of the key challenges for these bosonic modes for quantum information processing is actually these systems are sometimes lossy. At least so far, there will more or less will be some excitation loss happen to the bosonic system when you process information. And one question is, can we actually overcome these loss errors so that we can store information at least longer than the lifetime, than the cavity characteristic lifetime? So that's actually kind of one of the major challenges for the field with using bosonic system to process quantum information. And so, and one of the other challenge which is actually there is a no-go theorem saying that if you're just using those traditional like beam splitters, phase shifters, or even squeezers, there is no way you can correct such a loss error. So you need something definitely beyond those traditional methods that we use for the optical system in order to suppress those photon loss errors. So now, in order to actually overcome the loss error, we need first a bit more control power so that we can actually, in some sense, even be able to do like more control than just performing those Gaussian operations that kind of always preserve the positivity of the Wigner function. So that's why I'll first start with how to perform like a universal control over bosonic modes. Then in the second half of the talk, I'll talk about how to use these controls to achieve like a quantum error correction so that you can correct those loss errors and store information longer than the typical lifetime of these bosonic systems. So maybe to start with, I guess for the audience here, like also like when I was kind of undergrad here, also like doing postdoc, there's a lot of excitement about using cavity QED, which is the atom inside the optical cavity, which you actually use the nonlinearity of this atomic system, which it's a two-level system, which is it will saturate and even Rabi oscillate. So that's where the nonlinearity comes from. And that can allow you to control these bosonic cavity system to do lots of quantum operations. And similarly, actually in the solid state platform, the superconducting cavities, you can also use the Josephson nonlinearity, which shown in the lower left here. It's actually that when you have a Josephson potential, that you can actually create this aharmonic potential. And if you use the lowest two energy levels, which is the design of the transmon qubit. And moreover, in the cavity systems, you actually, in the superconducting cavity system, you can even just make a three-dimensional superconducting cavity, which with very little defects and so on, you can have a very long coherence time. So sometimes the people say we actually using the superconducting Josephson device to process and store information, but actually these cavities can have much longer coherence time than the superconducting device. So one question would be, can we actually store and even process information using these superconducting cavities? So that's actually kind of related to, okay, can we use the bosonic system to store and process information? So if you see on this, on the left-hand side, this is the device, which is of order like few centimeter dimension, which is a typical wavelength of a microwave at a few gigahertz. So you may see actually there are two, actually probably better point with the pointer here. So you can actually see that there are two cavities. One is for storage, one for readout. And then there's a semi-transparent chip, which is a sapphire chip, which hosts a Josephson junction device, which gives the nonlinearity for the control. And so for our talk, we're mostly interested in this one cavity, which is storage to store the microwave photon. And then there is this Josephson device, which we actually call the transmon qubit, effectively using the lowest two energy levels to control the bosonic cavity systems. So now, so for the cavity and this another two-level system, which you can think of as artificial atom, but when their resonant frequencies are very different, then basically they do not change excitations, but they only virtually kind of like couple to each other. So the effective Hamiltonian for this system will be cavity harmonic oscillator Hamiltonian and the two-level system. And then there is a dispersive coupling between the two-level system and your bosonic system in terms of frequency shift of the individual modes. So this Hamiltonian, this coupling term, you can think it as depending on the state of the two-level system, the E means the excited state. Then if it's in the excited state, there will be a frequency shift of chi for the oscillator. On the other hand, you can think that for the excited state of the two-level system, there is a frequency shift which is proportional to the number of excitations inside your bosonic system. So this is actually a very interesting coupling, and definitely it's beyond the quadratic form. So it's actually give you the nonlinearity, also give you the coupling. So one thing was to point out is that for the superconducting system, the dispersive coupling can be very strong. Strong in a sense, it's much larger than the decoherence of the cavity and the individual transmon qubit. So it's about 3 order of magnitude stronger than the cavity decay or the qubit decay. Moreover, with this system, you actually can have, like as I mentioned earlier, really long-lived cavity, about 10 or 100 times longer than the qubit lifetime. And you can also do fast, non-demolishing readout of the two-level system without destroying the state inside the cavity. So that's what this quantum non-demolishing feature of the readout is. And moreover, people have developed the fast electronic control with FPGA, so you can do real-time adaptive control for the system. So now if we look more of this system, Hamiltonian, then we may ask what are the control knobs we have. So basically we can drive the cavity or drive the qubit. So the drive we put in really depends on what's the frequency of the drive that you put in. So if the drive frequency is resonant to the cavity, then you can displace the cavity mode and the kind of inject excitation or take away excitation from the cavity. And on the other hand, you can also drive the two-level system with different frequency tones. And here I isolated these special frequency tones correspond to the two-level system shifted by an integer multiple of the dispersive coupling. So that you can think it as I have a selectivity to drive the two-level system only if there is a certain number of excitations inside the cavity. So I can do this selective drive for the system. So now the claim I want to say is that once you have these two drives, you can actually get a universal control over the joint cavity qubit system. So here is actually, let's go to first the rotation. Let's tentatively not worry about the cavity drive and also go to the rotating frame of the cavity. So basically the energy, you can think a cavity have 0, 1, 2, 3 excitations or more, and the qubit can have a ground or excited states. And because of the dispersive coupling, the excited state level of the qubit gets shifted by integer multiple of chi, depending on number of excitations in the cavity. And moreover, because the system is highly coherent, you can actually selectively drive this transmon qubit only if there are a certain number of qubits in the system, because you can spectroscopically resolve these individual transitions. Okay, so one thing we know about the two-level system is that when you drive it up and drive it down with 2 pi pulses, it actually will accumulate a non-trivial geometric phase. So this is actually, you can think it as a block sphere associated with this two-level system. You start from the ground state, you drive it to the excited state. Then the next drive, you shift the phase of your drive, and it will enclose a non-trivial area in the block sphere. And that corresponds to a geometric phase that imparted on this two-level system. And that geometric phase only happens if there are 2 photons in the system, then which means if I have 2 photons, I will accumulate an extra phase. If I have different photon numbers, then there is no phase accumulation. And the amount of phase accumulated is really controlled by the relative phase of these 2 sequential drives. So I can have a full control about the phase being imparted on this particular energy level with n equal to 2 photons. Moreover, I can simultaneously drive these different transitions, and that will accumulate different phases for different photon numbers, all controlled by my relative phase of the sequential 2 pi pulses. So that's what we call the selective number-dependent arbitrary phase gate, the snap gate. So with this selective control and also like a highly controllable of the phase imparted to the system, basically you can achieve a unitary operation, which is for individual photon number n, I can impart a geometric phase phi n, all controlled by my microwave drives. So if the phi n is proportional to n, it just corresponds to evolution of a detuning. If phi n is proportional to n squared or higher power of n, essentially or the Kerr effect. So all these nonlinearity fundamentally all comes from the fact that we have a two-level system in the system. Okay, but this effectively shows up that you can actually engineer so that your oscillator will behave highly nonlinearly. However, just with this kind of engineered this selective number-dependent arbitrary phase gate, it still not give us universal control because the photon number is still conserved inside the cavity. So in order to get more control, we actually reintroduce this displacement of the cavity so that you can shuffle photon around with different photon numbers. Then you see that all these energy levels are fully connected. And that's actually a necessary condition you have for universal control, but you can show it more carefully that indeed you have a universal control over both the qubit and the two-level system, so the oscillator. So here's just maybe to illustrate that we do have such a control. maybe first one thing to try is, can we create single photon on demand? Because that will potentially have useful application for quantum communication or other application or other uses. But here we can start from just a vacuum, and we displace the cavity. And here is the Wigner function of the cavity modes. And the upper panel shows the population distribution, where the arrows just indicating the relative phase between different population components. And the lower panel are just experimental data verifying that indeed the population satisfies the Poisson distribution as required, as predicted by a coherent state. So once we displace it, we can use the snap gate to dial the phase associated with the zero photon component. We just introduce a pi phase for the zero photon state, and the other components just keep the same. And you see the Wigner function suddenly has a negativity in there. And the population doesn't change in the distribution because the phase don't change population. But the Wigner function resembles the single photon Fock states. You just displace it back to the origin. And what happened is actually in the Wigner function, you get a single photon Fock state. And in the population, you can think that when you do displacement, there is a interference between different photon number states. And there are some components constructively interfere, like the one photon components, and the other components destructively interfere, and you actually get a single photon Fock state. So basically, combining displacement, snap, and displacement, you actually can create a single photon on demand. With the fidelity, it's not going to be perfect in this case. It's at least 99%. So it's already really good. If we do more such operations, you can actually make it even better. But if our goal is not just creating photon states, we want to perform some unitary operation, then here is an example. If you want to perform a photon number +4 modulo 8, then this is kind of the unitary you want to do. And then instead of sequentially doing cavity drive and the qubit drive, we can simultaneously drive both cavity and the qubit. And that actually becomes so overwhelming that we cannot do it by hand. So we actually use a computer to optimize the design. And it gives this complicated sequence of a qubit drive and the cavity drive with different colors for the real imaginary parts associated with the drive. And you actually, in the end, if you start from vacuum, you create a single photon, a 4 photon Fock states, which is consistent with the desired unitary to photon number +4 modulo 8. Okay, so this is the theory, and that's actually kind of the prediction, and they see like a good agreement. But one question is that, okay, suppose we can do photon state preparation or arbitrary unitary. Are there other more general operation we can do? Because we know that in reality, our quantum dynamics may not necessarily be unitary if we consider open systems. So the more general evolution actually can be arbitrary quantum processes. So what's the most general process allowed by quantum mechanics is it should preserve the positivity of the density matrix and also preserve the trace of the density matrix. So it should be called a complete positive trace preserving map, and which you can represent it as a sum over these k operators sandwiching the density matrix. So you can think that somebody is throwing a dice, that if the outcome is 0, 1, or 2, then you apply K1, or K0, K1, or K2 acting on the system. So this is called the cross-representation of the most general quantum processes. So if you have a D-level systems, you can always find a representation with no more than D square such cross operators acting on the system. So now, generically, how we create this, if you look at the textbooks, it will tell you that you need, if you for D-level system, you need a D square level ancilla, initializing the 0 state, going through a unitary which is D cubed times D cubed unitary. And then you throw with ancilla, you recover this system. So you can think that you need a D-level ancilla is because you possibly will have a D square outcomes, which correspond to the different branches you choose for the evolution. And this is actually pretty demanding. If you have a 10-level system, you need a 100-level ancilla to do that operation, which basically it's very difficult to do. But one thing which we find is probably you're not making the most use of the ancilla because you throw it away at the end. And what if you can reuse the ancilla? What is the minimum level of ancilla that you will need? So if you have a 1-level ancilla, it's trivial. It means you don't have an ancilla system. So the best guess will be you need 2. And it turns out that with a 2-level ancilla, you can already control the full system. But you need to repeatedly use it. So here is the scheme. So if you have D-level system with a 2-level ancilla, so you can think your system is your cavity and your ancilla is your kind of a transmon ancilla, then you can basically let them couple first, and then measure the ancilla, you get one classical bit of information. And then condition on one classical bit of information, you determine what unitary to apply in the second round. Then you measure the ancilla again, you get the second bits of information. And then you repeat this the third time, you get 3 bits of information to determine what to do in the next round. So after this log n rounds of iterations, where n is the number of cross operators you need to apply to the system, it actually will give you enough variety so that you can actually implement this quantum channel. So you can show this is information theoretically kind of like a most efficient way to actually get such a depth of circuit to implement such a general quantum process. And what's more important is, if you look at this circuit, you just need to couple the system with ancilla and do some measurement and feed forward. So we already know how to couple the system and ancilla because we know there's a universal control over your bosonic system and the 2-level ancilla. And moreover, you also know how to perform these quantum non-demolishing measurement over the ancilla, and also use FPGA control. You can do feed forward control so that you will be able to implement the entire sequence if there's enough memory for your FPGA to store what unitary need to be applied. For this, you can think of it as a binary decision tree for the entire process. So I want to point out this is extremely powerful for this operation because it can implement any physical processes. It can sort of like simulate any physical processes that you can imagine for these D-level systems, because that's the most general process allowed by quantum mechanics, which is preserving the trace and preserving the positivity of the density matrix. So just as a summary of what I've talked, basically with this universal control, you can prepare arbitrary states. You can do arbitrary unitary, and most generally, you can perform arbitrary quantum process. And this arbitrary quantum process, including quantum error correction, because quantum error correction is essentially a quantum process that extracts entropy from the system while preserving the encoded information. So far, we've been mostly talking about the control, which I would say it's a unitary control, because you use the Hamiltonian evolution to evolve to some point, and then probably do some measurements if needed. But there are actually more general controls you can do besides unitary control. You can also engineer the dissipation, or combine the unitary with the engineered dissipation. So one example you can think of is that introduce some projection always to some certain subspace. So like Zeno dynamics. But this usually with how Zeno is, Zeno fix it to a certain state, but we can also project it to a certain subspace. Then your Hamiltonian evolution, it may have a tendency to push it out of the subspace, but your Zeno projection will push it back to the subspace. Then you actually will get a non-trivial evolution within that subspace. And it turns out that can also be useful for our universal quantum control. And moreover, even a bit more surprising is that just using dissipation, you can also achieve universal control. So here, for the sake of time, I may not go to detail, but the key point is that you can use sort of engineered dissipation to let the system go in some like closed loop. But with that closed loop, it actually have a non-trivial kind of a holonomic evolution. Then that will give you the desired operation. So, but all these are actually possibilities to do these controls, and which actually later on, so we already talked about the first one, which will be useful for error correction. And later on, we also will talk about how to combine these drive dissipative system. You can also do quantum gates. So now that's all about quantum control, the most general control, either using unitary or using dissipation. Now let's actually move to the second part, which is how can we use these controls to perform quantum error correction to correct loss errors. So the essence of error correction is actually to introduce redundancy so that you can correct errors. Because if error happens, you actually go to some error space, which is orthogonal to your original code space, so you can differentiate different errors and then restore it by some correction operation. So for a qubit system, if you only have 2 levels, then there's not much redundancy or extra redundancy you can introduce. So you have to use multiple copies of 2-level systems to give you the redundancy to do error correction. And for 2 levels, when the more 2 levels you have, the more likely you will have individual qubit errors you need to correct. However, for harmonic oscillators, it's actually different. Because first of all, we know from our quantum mechanics class, for harmonic oscillator, you have infinite number of energy levels you can have, right? Because the raising operator kind of never ends when you keep raising it. On the other hand, for harmonic oscillators, the errors are very structured. So if you have photon loss errors, every time you just reduce the excitation by 1. If you have dephasing errors, you actually preserve the number of excitations. So basically, in the number basis, you will see that the photon number don't change too much. And if you think in the phase space, the Wigner function actually only distorts locally. So there is this structure or locality of the error so that you can actually take advantage of when you design quantum error correcting codes. In particular, if you consider loss error, every time you lose the excitation, it changes the parity of the number in the system. So if you can measure parity, you might be able to detect individual loss events. So now, actually, we're not the first people who look into bosonic error correction. There's a zoo of bosonic error correction code. Okay, people have looked at it in the early, in the late 90s, and when actually like here is a kind of a distribution of the new codes that are being discovered, and you see that in the early 2000s there's a burst of bosonic codes because at that time people think about linear optical quantum computing with the detector nonlinearity, and more recently we look into actually superconducting Josephson nonlinearity to control the bosonic system. So for photon, the encoding includes using photon numbers, or using coherent states, or using higher level Fock states, or positional momentum, or hybrid coding. So the focus of this talk, we would like to check if we can use a single bosonic mode to control and to correct photon loss error. So before we get to the quantum case, actually, it will be inspiring to look into what we do in the classical domain. If we send a single bosonic modes, can we correct loss errors? So one thing we know about the coherent state, even just think about the harmonic oscillator, is it will characterize by just a complex number, which we sometimes call the complex. One is the amplitude. The complex phase corresponds to the phase of the harmonic oscillator. So if you go through a lossy channel, this complex number alpha, the amplitude may change, but the phase is still preserved. And this is actually crucial. It allows us to do something called the phase shifted keying. So you encode information in the phase of a coherent state. If it goes through a lossy channel, as long as it does not go all the way back to vacuum, there is still some distinguishability if you encode in different phases, and that allows you to encode classical information in the phase. For example, here you can encode 0, 1 with these 2 blob encoding. If you have 4 phase blobs, you can encode 2 classical bits, and if you have 8, you can encode 3. And this is a very successful technology widely used in Wi-Fi and Bluetooth. Now, the question is, can we extend this to the quantum domain? So one thing is that we should keep in mind that sometimes redundancy will be helpful to encode information and correct errors. If we, for example, if you have 4 coherent states, in principle, there's a 4-dimensional Hilbert space to encode 2 bits of information. And if we use that 4-dimensional Hilbert space to encode 2 quantum bits, then we actually lose the capability to know whether or not there's a photon loss. So in order to be able to detect photon loss, it's actually better to be less ambitious, just encode 1 quantum bit of information in this 4-dimensional Hilbert space. And you can encode it in the even photon subspace, which can be spanned by the coherent state symmetric combination of alpha and minus alpha, which one way you can see it, it's an even photon number, is the even photon number correspond to 180-degree photon rotation. And you will find that in the phase space, and this is actually symmetric under that, which means there's an even number of photon in the phase space. Or you can expand the photon number basis to verify it has even number of excitation. Similarly, you can do the I alpha and the minus I alpha superposition. That also can be another logical state. So this is actually the CAD code, which encodes 1 quantum bit of information using a harmonic oscillator and only encoded in the even photon subspace. So now let's see how we actually perform logical operation, or how we actually protect the logical information. So suppose we encode the logical 0 and logical 1, and these are almost orthogonal when alpha is large enough. So now suppose you have arbitrary states to start with, say C, G logical 0 and CE logical 1. Then when you lose the 1 excitation, it goes from even to odd. And moreover, the coefficient CE inherits an extra phase I, because when you apply annihilation operator on coherent state alpha, it will pull out the whole entire quantity, including the phase in there. Then when you lose 2 excitation, you go back to even, 3 go to odd, and 4 excitation, you go to the original state. So that's the circle of life for such a state. And notice that every time you lose a photon, there's a parity change. So if you can monitor the parity and you monitor it frequently enough, then you will be able to identify every photon loss. And that actually can correct, or that can allow you to correct single photon loss error. So first you can detect. Moreover, the way you can correct is that once you know how many photons are lost, you can use that to interpret what's the encoded information. And that's the way it allows you to restore the information. So another type of code in case really, and here is the minimum code that allows you to demonstrate you can correct the single photon loss error, which is called the Killen code, actually invented by Steve Gervin. And so this code is that you can prepare a superposition of 0 and 4 photon states and a Fock state 2. Those are the 2 logical basis states. They all have even photon number, and average photon number is 2. So which means any linear combination or superposition or mixture of the 2 all have 2 photons in the system. So they're equally likely to lose a photon. So just based on whether or not they lose a photon, you cannot use Bayesian to infer which state is more likely. And moreover, if you have a state which is 0 and you lose a single photon, we recall that in quantum mechanics, this annihilation operator has a square root of n, we call the Bosonic enhancement factor, and that will give you square root of 2 times the 3 photon state. And if you have a 2 photon Fock state, you lose a photon, you can get the square root of 2 times the 1 photon Fock state. So now if you have a logical 0 and logical 1 as superposition, then you lose a photon, you actually still get a logical, the Fock photon, 3 photon state and 1 photon state with the same superposition, which means, and also this is orthogonal to the original state, which means you can find a unitary transformation to convert it back to the code space to restore the encoded information. And you may ask, what if I have 2 photon loss? Unfortunately for this code, it doesn't work, but I can come up with a more sophisticated design called the binomial code, which the coefficients are just the square root of binomials that can correct multiple photon loss errors. So now that's kind of a second type of code if you really like to think in the photon number basis. And there is actually another type of code which was actually invented by John Preskill together with Daniel Gottesman and Kitaev. That was actually code invented more than 2 decades ago. That was called the Gottesman-Kitaev-Preskill code. And it actually has an analogy to the classical code called the quadrature amplitude modulation code. So suppose you know the amount of loss of your bosonic channel, then basically you can just use both amplitude and phase to encode information. Since you know the loss, you can actually predict based on what you measured to what is the original amplitude. So that allows you to encode more information and fill up the entire phase space as long as you can distinguish these different blocks. And the quantum version is that you also want to introduce redundancy. So instead, you just encode 2 quantum bits of information by choosing the proper superposition of these coherent blobs. And of course, you need to be careful with the spacing of the blobs in order so that you can design the stabilizers, which kind of these logical states are co-eigenstates of these stabilizer operators with eigenvalue +1. So that by measuring the stabilizers, you will be able to know whether or not you have additional noise introduced to the system. But once you have that, this is actually give you a new type of code, which turns out to be really, really efficient. So one thing is that if you look at the stabilizer, it corresponds to displacement along the momentum direction or displacement along the position direction for your oscillator by a fixed amount. And that means you can effectively measure the position or the momentum modulo some constant. So that's kind of a back action evading. So that's kind of so that you can evade this Heisenberg uncertainty principle, but not to measure both position momentum, but you measure position and momentum modulo certain constants. So that's actually like very useful later on if you want to design a code to measure additional noise. So one question would be, okay, so far I talk a lot of code. CAD codes, binomial codes, and the GKP code. Here I'm just plotting the Wigner function of the projection operator of these codes. So you can think that whenever I talk about the codes, sometimes it's always confusing. Say, what is logical 0? What is logical 1? Then I say, don't worry about it. Just get the projection operator to the logical space. And then that gives you a unique signature or we can call it fingerprint of the code. So these different Wigner functions correspond to different code. So one natural question is, which one is a better code that correct errors? Okay, so then we have fixed the code, fixed noise channel. Then what we need to do is optimize the recovery. And this is actually like turns out if we introduce the appropriate fidelity called the entanglement fidelity, then you can actually do a convex optimization to find the optimal recovery. And this is actually the performance in terms of the entanglement fidelity as a function of the loss probability of individual excitations in the system. And you see that actually you get the cat code and binomial code, which started decreasing, but the GKP code works really, really well. It can even correct up to even 30% or more like loss errors. And if you make they both kind of like goes really well approaching 0, approaching 100%, but you plot the infidelity at the log scale versus the loss rate, you find the GKP code can correct actually like a 10% loss and restoring the fidelity with 99.99%. This is actually a really like, I would say like impressive performance of the code. And moreover, I'm not talking about like a state with infinite energy. I'm just talking about the state with average about 10 excitations in the system. So that shows that indeed that potentially like maybe if there's about 10% loss in a bosonic system, you can design a good code that in principle, it can correct all these errors. Of course, this is by no means that, okay, we should always go to GKP code, even though John's here. It just says that ideally, this will give you the good performance. But in practice, there's also a question about, okay, is it feasible to implement these error correction schemes? Or does so far I'm only considering photon loss errors. There could be dephasing errors and other errors. Maybe for the other errors, maybe you need to optimize your code choice for those different codes. Yeah. But another thing is actually, maybe one might ask, what is really the best code? And actually, former student Kendrew also look into this problem by alternating optimization of the code, encoding and decoding. And when alternating optimization, you will actually find that start from some random coding, you start to see some pattern emerge. And this pattern is actually correspond to the GKP state for a single oscillator encoding. And notice that pattern is a hexagonal, it's not a square lattice. It's actually correspond to a more efficient packing than the square lattice. That's why actually the hexagonal lattice can work even better. Yeah, so, but the key message is still like, actually it has a great potential to correct a significant loss error and still store and protect the encoded quantum information. Okay, so now we talk about on the theoretical side, what's kind of maybe the best code for loss errors. And then experimentally, like, can we actually demonstrate some of these error correction, bosonic error correction scheme? So instead of doing the GKP code, probably it's easier to think about maybe the easier code to start with is the cat code, since it only have 2 or 4 components. And just recall for the cat code, the key ingredient is we need to monitor parity so that we can detect single photon loss error. And then the question is, how do we monitor parity? We cannot use the photon detectors or other counters which will destroy the encoded state. We just want one bit of information, which is parity. And in order to do it, it's actually the idea is actually you can do Ramsey experiment, because what one can do is we already have a 2-level system that coupled to the bosonic system with dispersive coupling. So we can actually use that 2-level system to make a query of the bosonic system to know whether or not there's even or odd number of photons in there. And the way to make a query is you first prepare your 2-level system in a symmetric superposition of G and E states to start with, which is what this pi over 2 pulse refers to. Then you let it evolve under this Hamiltonian for time pi over chi. During this evolution, each of the photon will impart a pi phase shift to the excited states of the 2-level system. So if you have even number of photons, there will be integer multiple of 2 pi shift for the excited level, which means there is essentially no effect to the excited level. If there are odd number of photons, there will be odd integer multiple of pi phase shift to the excited level, which will give you a -1 phase for the excited level. So if you start from a symmetric superposition of G and E, you will end up in either symmetric or anti-symmetric superposition of G and E, depending on the parity. And when you measure the 2-level system, you know the parity of that system. Okay, so then basically you can put all these together with the code the protocol to detect parity, and then you can do the decoding to get the information. So for comparison, you can actually do the experiment with the different memory time, and the vertical axis is the process fidelity. And in order to show that error correction help, you need to compare with the best scheme without error correction. For photon loss, the best scheme is to have a 0-1 encoding, because that minimizes excitations. And it turns out we also did the optimization to verify that indeed this is the best encoding. And that's the performance for that particular experiment with about like 300 microseconds. Then once you introduce the encoding, but don't do error correction, the performance degrades because you have more photon in the system. It's more likely to lose photon. But once you put in the error correction, actually this red curve shows that actually effectively the lifetime gets extended to the level comparable or even slightly higher than the best encoding you can get without error correction. So one question people will ask, well, what limits the lifetime for the encoded scheme? Because if we do error correction, we do it frequently enough, then in principle, we should be able to further extend the lifetime if we do it frequently enough. However, there's a price we have to pay when we do error correction. It's because whenever we do error correction, we actually may introduce errors from our operations. In particular, here when we do error correction, we introduce an ancilla, which is also lossy itself, so that there's a chance to introduce a few % of error every time we perform error correction. So that limits the frequency we can actually, how frequently we can do the error correction, because you'll get diminishing return if you do it too frequently. Now, if we look at further, the dominant error for this case is actually there is excitation loss when you do in this procedure, when you try to acquire phase for your two levels using your two-level system. So this is a dispersive Hamiltonian. So if there is an excitation loss in the halfway, so the cavity will start to accumulate in phase, and then suddenly the qubit, the transmon decay, then you're kind of accumulating a random phase if you don't know when this decay happened. So that is actually where the key reason that we start to introduce dephasing when these ancilla systems start to decohere. So the way to get around it is actually, can we actually introduce some additional redundancy for the ancilla so that we'll be able to first detect whether or not such a decay happened. And second is hopefully that decay will have some back action that we can actually recover. The way to do it is actually to use a 3-level ancilla, which reminded at the transmon device is the harmonic oscillator with this cosine potential. So you can use the second excited level of the ancilla and use the knowledge that the ancilla also lose excitation one by one. So if we just encode the information using G and F, then loss of excitation will only convert it into the energy level decay from F to E. So first, if you measure the system, this ancilla end up in the E, we know that the loss must have happened. Moreover, you can also engineer the Hamiltonian for the system and ancilla coupling so that E and F will have an equal amount of frequency shift to your oscillator, which means that it doesn't matter how long you stay in the E state, how long you stay in the F state, the oscillator will accumulate an equal amount of phase. And it doesn't matter when the transition go from F to E happen, the oscillator will still accumulate an equal amount of phase, which means the oscillator will get a unitary evolution, even if decay happened, even if we don't know when the decay happened. So this is actually the key concept that we actually can use to do something we call the error transparency. Or mathematically, it corresponds to the jump operation, go from F to E, commute with the Hamiltonian, which has an equal dispersive coupling, dispersive shift from energy level E and F. So this is what we call the error transparency condition, which is an example that allows you to kind of use a noisy ancilla to measure a cleaner system, but don't suffer from the decoherence of the noise, because you engineer the Hamiltonian so that some ignorance of when the relaxation happened does not introduce additional entropy to the system. So generally, there's a question about like, if I have a central system which is cold and I have an ancilla system which is noisy, but to have more control, can I actually get a full control over this central ancilla system, but not limited by the ancilla noise? And the answer is actually yes. And but it needs to engineer the coupling between the system and the ancilla carefully so that it satisfies some condition we call the path independent condition. So generally, you think that it's an open system ancillar evolution with some like open system dynamics. And you can think as like a path integral that you will have some different trajectories for the ancillar to go from some initial state and then finally measured in the final states. There are different trajectories, but we don't know which trajectory really happened. But it is okay if all these trajectories are equivalent to the same unitary evolution. Because if that's the case, then we actually say we don't care about which trajectory happened because this whole system undergoes the specific unitary that only determined by the initial and the final state of the ancillar. And this is what we call the path independent condition, which is actually the earlier example of error transparent condition. It's just a special case, which allows you actually to even not only do measurement, but also to control this ancillar, this central system using a noisy ancillar. And we actually demonstrate you can do some snap gauge for the central system with a noisy ancillar, not limited by the decoherence, the relaxation and dephasing of the noisy ancillar. Yeah, so maybe for the sake of time, I will not go to details on this, but here the bigger picture is that generally like there is this challenge of how to do this QND measurement of all the way up to do fault tolerance. And there has been kind of this, in the past decade, there have been lots of advances using these quantum system to do the control and demonstrate some proof of principle like a robust quantum control. Yeah, but again, just if we step back, take another look of what we're doing, is basically we have what I've talked is focusing on how to do discrete quantum error correction. So discrete means that every once in a while you start to look if there is error happen. If no error, you move forward. If there's error, you try to correct or update your description of the system. However, there's a more general way of another way of doing the error correction is this continuous quantum error correction. So instead of like discretely do the measurement, you can either engineer the dissipation or perform a Hamiltonian protection, kind of introduce either a dissipative gap or Hamiltonian gap to protect the system. So the uniqueness of this is that with a continuous error correction, you can actually get some feature which called the error bias performance, which is certain errors can be exponentially suppressed, while just leave some other errors which probably only increase linearly with certain parameter of the system. So that if you can get an extremely high bias of error, then you can probably rely on the next level of system error correction to correct the remaining error, like what we do in the classical domain, just using some repetition code. So this has the potential to be hardware efficient because usually error correction is challenging. We need a lot of resource to do it. And so let me just maybe focusing on one example of how to use engineer dissipation to actually to do bias preserving like coding. So the key idea is the following. So we can engineer dissipation so that to stabilize to these two fixed points with coherent state, alpha and minus alpha. And if you think in the classical domain, it's more like there's a flow diagram can push it towards these two fixed points. And moreover, it actually can still maintain the superposition when you push it towards those two fixed points. Or think in quantum ways, actually stabilize a subspace which is spanned by those two fixed points. So now there are actually like a lot of developments that to either use kind of like engineer dissipation or using KerrCat or using color KerrCat, which the latter two actually like also like a collaboration with actually the Amazon AWS effort here, which we can stabilize these codes. But one of the challenge for this, which I skipped some of the details, is that we want to do fault-tolerant quantum computing in the long run. And if you want to do fault tolerance, you actually cannot accumulate too much error in this PZ. And also PX, PY should be exponentially small. But for this type of schemes, typically you need to have a very, very strong, good dissipation to suppress the bad dissipation. And typically the good dissipation needs to be maybe 1,000 times stronger than the bad dissipation in order, at least 1,000 times stronger in order for this system to work so that next level of error correction is still below the error correction threshold so that you can do fault tolerantly, assuming that you can do the full fault tolerance at the next level. So the one question is, can we further relax this requirement so that the good dissipation will not be that demandingly strong? Because that's actually one of the major challenges like for the efforts that you really want to make such engineered dissipation to work. And it turns out that we have a way to maybe relax this factor maybe by a factor of 10. And the idea is actually you need a better choice of the code. So maybe for people who work on the CAD code, this is probably like a maybe one way of thinking of it is that for the CAD code, you actually have a Poisson distribution because it's just the coherent states. And you actually have photon numbers, which are pretty big because the Poisson distribution pushes the photon out. But when you do, one thing we can do is similar to kind of we do in LIGO, is to introduce squeezing. Because once you squeeze the CAD code so that the standard direction in the phase space gets squeezed, then the average photon number actually will reduce. And until to the point that the other quadrature gets anti-squeezed too much, so then the photon number will increase again. So since the photon loss is the dominant error, you want to make sure actually you have a coding with the minimum photon number, then actually the squeezing can help you first to reduce the photon number. Moreover, once you have the squeeze CAD, you will find that if you have photon loss, you actually, the state that you become, it's no longer the other code word. It actually will have some excitations effectively as a gauge degree of freedom. Then you can actually engineer the dissipation to suppress that error and even correct it. So different from a CAD code, you actually can not only reduce the average photon number, you can even correct a big fraction of photon loss error, which they cannot. So that's first improvement number one. Second is actually the chance you can correct the bit flip error will go from exponential to double exponential. And moreover, the engineered dissipation gap will also have a scaling which scales as the photon number squared. So here I'm going a bit fast, but the punchline is it's better in all three aspects. And more importantly, with a large dissipation gap means that you can do the operation faster so that in the end, you can improve the threshold requirement in terms of ratio between bad and good dissipation. So we want this number to be as large as possible so that we don't need very demanding good dissipation. And for the squeeze CAD, for the original CAD, you need that number to be around 10 to minus 3. And then here you can actually push that number to be around 10 to minus 2. If you do surface code, for repetition code and next level coding, it will actually also improve almost by order of magnitude. So and that's actually, it's exciting that there's a way to maybe make this more feasible in terms of the strength of your engineered dissipation. Yeah, so maybe for the sake of time, I'll just say, okay, if we look into the paper, we actually have some scheme to use a superconducting platform or even using trapped ion to implement such an engineered dissipation, which hopefully it will be feasible in some experiments. So far I talked a lot about kind of using Bosonic error correction for computing, but it can also be used for communication. And one thing which at least when I was here, I took a class from Bob McLeese talk about the classical error correction. There are just two things. One is the Shannon coding theorem. The other is there are good codes which can potentially approach this coding limit, including this the 5G, the codes using 5G technologies. And now in the quantum domain, there's actually an open question about what is really the good quantum channel capacity for many channels, and what are the good codes and that can potentially achieve the channel capacity. And actually, we look into some of the codes that the GKP codes turns out to be even correcting photon loss error. Asymptotically, it may actually also have the same scaling as the quantum channel capacity. We get the upper and lower bounds because we don't know what the capacity is, but the GKP codes have the same scaling when the photon loss is low. And moreover, the Bosonic codes can also help you to demonstrate sending quantum information from one place to another using some Bosonic channel. And the surprising thing is, even if the channel is in some thermal states, it's okay. You can still send quantum information through, as long as the information, the mode used to send the information don't mix with the thermal background, which is actually mostly true if the channel is it has a low loss, but the channel can be in some thermal states, then your mode actually do not mix with the thermal background. So all you need to make sure is that when you catch that excitation, you need to catch that particular mode so that you don't suffer from the thermal noise. But in that case, even if there's thermal noise, you can still use some quantum error correcting codes to correct it. So maybe, yeah, here's just the illustration. Suppose you pitch a particular mode. All you need to do is just to catch that mode. Don't worry about the other thermal noise in the other modes. So that's in some sense a bit surprising, but if you think more carefully, it's a linear system. In fiber communication, we always do that in the classical domain. Yeah, so one thing which is, for example, kind of recently in in Switzerland, people did this like a 5-meter long, like connecting two diverging fridges. They recently even did a 30-meter long experiment and testing violation of Bell's inequalities. And you can imagine probably you can pitch a quantum state and send it over between different buildings. Yeah, so I think I probably just have maybe 2 more minutes about two things. One is about like a quantum metrology. And since here's Caltech, definitely people are very familiar with gravitational wave detection, and which kind of the first event around 2015. And also at the same time that there was earlier mentioned about the quantum error correction. So actually around that time that John and I had a discussion of can we actually use error correction to help LIGO to improve sensitivity. And unfortunately, it turns out that we actually get approved was by Susu Zhou, she's also in the audience here, that say this doesn't work. And she give a reason. And then when we generalize, say, actually get a necessary sufficient condition, under what condition error correction can help you to protect the encoded information, not limited by the decoherence of the system to get a Heisenberg scaling. So the key idea is that if you have noise in the system, then the noise operators will span a operator space. And that operator space will be contaminated by noise. And if your signal is in that operator space, then you actually will be scooped because there's no way to tell whether it's signal or noise when the noise becomes strong. However, if your signal has any part which is not in that noise space, then you will be able to pick up that orthogonal part, and that will give you the Heisenberg scaling for quantum metrology. Yeah, so maybe I probably will skip that example with you can actually sense the Kerr effect even if you have photon loss. The construction is actually using this binomial code, the Killen code, which if you look at the photon number variance, they are different. And then if you have photon loss, you can actually do the error correction to restore the original superposition. So in the logical space, you can still have a unitary evolution to achieve the Heisenberg scaling, even if there is a photon loss. Yeah. So so I think I probably will just skip this last part, which is about like how you do like encoding a harmonic oscillator into oscillators. But the key idea is that you can just introduce the GKP ancilla. As I mentioned, the GKP ancilla sort of allows you to sort of evade the Heisenberg uncertainty principle, so that effectively you can measure both position momentum quadrature with modulo some constant. But with that, you can sort of like do some combination of codes with that GKP ancilla with your bosonic mode. When you do that encoding, you can actually mix the noise over the system. And then later when you measure when you undo the decoding, you measure GKP ancilla, you can actually extract more errors and also correct this additional additive or even loss errors. Yeah, so maybe let me probably like stop here. And basically the key message is basically we can use the bosonic error correction to help us to do a lot of things, not just computing. We can also do it for communication or even some applications of sensing, and assuming the noise is not too bad. And the signal is also not mixed by the noise. And also you can even use it for some of the simulations and so on. Yeah, so finally, I'd like to thank the collaborators. There are a lot of experiments involved, and also like some of the work which I didn't have a chance to talk about, including like quantum random access memories and also other quantum network things. But for the squeeze cap is actually mostly by Chen Xu and Jerry Zheng, who actually come up with well, in some sense, we were kind of partly scooped by the other group, come up with a squeeze cap code, but we actually found a way to demonstrate it actually can do a much better job in terms of the scaling for the fault tolerance. Yeah. Okay, with that, I'd like to thank you for your attention. Yeah.
All right, thank you, Liang, for the beautiful and inspiring talk. But I'm a little disappointed you didn't make use of this bosonic mode, which I painstakingly set up for you. Well, we do have time for a few questions. Well, I can start. There's another way to do error correction that doesn't use bosonic mode. I'm curious about your view of the future. If I can make transmons good enough anyway,
Mhm.
I can just, you know, have only qubits.
Yeah.
And do error correction, say, using the surface code, which Alexei Kitaev kindly bestowed upon us. Do you expect that to really scale up fault-tolerant quantum computing, we will need to go the route of making use of codes in bosonic modes?
Yeah, well, I think at this point, it's still hard to say because indeed the transmon is actually getting better and better.
Mhm.
And so indeed, it's also a bit non-trivial to construct these bosonic codes, right? But so in that front, for computation, I think it's a bit, it depends, like how the efforts goes with bosonic codes and how the development of transmon can happen. But they're definitely like but bosonic code does have the advantage that maybe at the next level coding, it can be a bit more efficient because errors has a nice structure, which the traditional qubit code, it actually do not have this noise bias, or even if it does, when you do quantum gates, it will break that asymmetry.
That's the case for GKP.
Yeah. So now for the, but on the other hand, bosonic code also has its unique feature, this for communication.
Mhm.
We always use the bosonic, this modes for communication. We don't send spins or send electrons, we actually send photons, right? Or phonons, those are bosonic modes. And if we want to really achieve the channel capacity for those bosonic modes, the bosonic code is actually the choice. So and it's probably maybe when you start with, you actually don't worry about those modes. You just actually waste a lot of modes to send just a single excitation. But later on, when we get better control of these technologies, probably you want to maximize the channel capacity, like what we do with nowadays with Wi-Fi and Bluetooth and or even the 5G networks. We actually, I think in that case, you probably want to use the bosonic codes.
In principle, I could send single photons, but you're saying to get a high communication rate.
That's right.
Bosonic modes would be right.
Yes.
Other questions?
Yeah, so I have a question about the display plan.
Yeah.
In particular, it's about the implementation of this two-photon voltage, I guess, required, like,
That's right.
And so the standard way to do it is to get this use 4-way mixing to get this non-gain factor proper like each then it like
Yes.
But that itself could that be some sort of fundamental limitation of the time scale in this so that's a higher order factor.
Yeah, so I would say like that's actually a good point. That so currently I'm saying like, okay, we just look into the strength of the good and bad dissipation, right? But where do we get a good dissipation? It comes from other Hamiltonian controls and some other control dissipation. So that ultimately this will be, I think, fundamentally limited by the strength of the Hamiltonian control we can put into the system. So fortunately, when we look into this the superconducting circuit designs, it turns out that actually still give us a good, like a favorable, reasonable parameters, which I think we think are feasible with the experiments. Yeah. So and sometimes also with the trapped ions, and there's a way you can use the extra levels so that you can decompose the high order non-linear jumps into different steps. And each step you go from level 1 to level 2, you impart this the first part of the dissipation. Then the next step impart the second part. So actually, in that case, you can actually already have a very systematic way to construct very complicated jump operators. Yeah. So, but the challenge for trapped ions is that it's a good thing. Okay, they already have really good qubits, so they can just use their internal degree of freedom to encode information. But I think the hope is that maybe at some point, the bosonic modes or motion of the ion can be so well protected with such a high bias. So probably at some point they can take off and say, this is a better choice that probably you can do more reliable information storage over the bosonic degree with the motion of the ion. Yeah, which I think the Jonathan Holmes group has did some nice experiments with the GKP code with the trapped ions. And also for their case, the error model is mostly dephasing. And it turns out that, as I was asking Jonathan, say, why not just do the CAT code, because it's a more natural code to correct the dephasing error in trapped ion. And yeah, I hope that, okay, he will try some of these squeeze cats at some point.
Yeah. Over here.
Figure first, an arbitrary quantum process using a single episode.
looks, in spirit at least, like these holographic quantum product states that allow you to do arbitrarily large number of qubits with a single wire or one wire. Is that just sort of an analogy, or is there actually something actually really?
And yeah, well, I think there may be some connection, but here the key point is that effectively you need that many steps of operation, right? And if we pull them apart, essentially you need another effective ancillary systems, which is of a dimension d squared. Yeah. So maybe there is some counting that may be similar to that case. Yes. Yeah. So effectively you kind of, but in practice, that is currently qubits are still expensive. If you can refresh and reuse the qubits, it's actually a more cost-effective way to do such operation. Yeah.
But it's probably the exact speed of the same thing.
Yeah. Yeah.
One more.